I'm here to answer the question of how can we protect Earth from asteroid impacts? And when we think of asteroids, you probably think of kind of a big rock flying through space. And that's basically what an asteroid is. And if you try and kind of visualize an asteroid, what you probably see is something that maybe looks a bit potato shaped. That's what asteroids kind of look like. But the thing is, when you study an asteroid from the Earth and when you're looking at one through a telescope, you don't see it to this level of detail. And in fact, we're looking at an asteroid right now, but you just don't really know it. So when you look at an asteroid from Earth, it can be a little tricky to actually find it. So this is actually a photo that I took with a telescope about 3 weeks ago. It's a telescope in the Canary Islands, so of course I can't really go there at the moment, so I had to do all of this remotely. Missed out on a nice holiday there. I mean, important business trip. And what we're seeing here is what this telescope could see, and it's basically the same thing you see when you look up at the night sky, just more zoomed in. So these dots are stars, and the black space is, well, space. But hidden amongst these stars, there is actually an asteroid. And that asteroid is this dot right here. And the reason that we can see asteroids at all is that they reflect light from the sun. So you may have heard that we can see the moon because we see sunlight reflected from the moon and then it bounces back to us. And that's exactly what happens with asteroids. So when you point a telescope at the sky and you see an asteroid, it is just a point of light in the sky. And this asteroid that we're looking at here is one called 1950 DA. And this is actually a very important asteroid because it's currently ranked as the most dangerous asteroid that we know of. The reason for this is it's quite a big asteroid, so if it hit us, it would be, well, a very bad problem, or a very big problem, I should say. And it also has a reasonable chance of actually hitting us, although for this asteroid, its potential impact date is about 800 years away, so it's not one to worry about too much. But why do I look at asteroids like this? Why am I taking pictures of asteroids? Well, as Patricia said, I am a PhD student at the University of Kent, and I study asteroids. The research that I do is focused on looking at the way that asteroids spin. More particularly, I'm trying to detect changes in how quickly asteroids spin caused by radiation from the sun. I'm not going to go into too much detail about that during this talk because it's not quite as exciting as asteroids crashing into the Earth or potentially crashing into the Earth, but I'll intersect my research where I can because the stuff that I do does contribute to planetary defense or preventing asteroid impacts. And of course, the research that I do does involve a lot of using telescopes. I can't travel to these telescopes anymore, have to do it all sitting here on Zoom, just like I am right now. But I describe myself as an observational astronomer because a lot of astronomers these days just sit at a computer all day and play around with computer models, where I actually go out and still take data and do things the old-fashioned way, so to speak. So for this evening's talk, I'm going to actually break down this question into some smaller questions. And the first is, are asteroids actually a genuine threat? So as Patricia said earlier on, we've probably heard about them in sci-fi and we've seen the movies or heard of the movies where asteroids are going to crash into the Earth and cause these massive apocalyptic scenarios. But is that something that could ever really happen? Although if you're here listening to me today, you probably already have some idea about whether or not that's true. Then I'm going to talk about how we actually find these asteroids and how do we detect these asteroids and how do we know if they're actually going to hit the Earth. And then I'll look at perhaps the most exciting part, and that's, could we stop an asteroid from hitting the Earth? So part one, are asteroids a genuine threat to us? So there are lots and lots of asteroids out there in our solar system. There are hundreds of thousands of them that we know of, but just for tonight, I'm only interested in near-Earth asteroids. And a near-Earth asteroid is just an asteroid that comes close to the Earth, which means its path as it travels around the sun kind of overlaps with our own orbit around the sun on the Earth. So to date, we have discovered 25,000 near-Earth asteroids. And out of those 25,000, around 2,000 have been flagged as potentially hazardous. And that means they come close enough to us that there is a chance that they could hit us. And it also means that they're big enough that if they did hit us, it would do a bit of damage. So if you look at this graph here, and I promise not to show you too many graphs tonight, you can see that this is the number of asteroids, total number of asteroids discovered right up until around last week. And you can see since around 2000, we've really gotten good at discovering asteroids. And most of the asteroids that we're discovering are smaller asteroids now. So when you look at the biggest asteroids, which are bigger than a kilometer across, we've already found 90% of them. So these really big asteroids, they reflect a lot of light, and so they're really easy to find. But we still have a long way to go to find all of these smaller asteroids in our solar system. And smaller asteroids are more common than big asteroids in our solar system. So what happens when one of these asteroids actually hits us? Why is it something to worry about? Well, this is what happens. So this is something called Meteor Crater. I know it's a very creative name. And this crater comes from an asteroid impact that happened 50,000 years ago. This crater is around 3/4 of a mile across. But the asteroid that created this crater was just 50 meters across. So even a relatively small asteroid can cause huge devastation. If you imagine something like this happening in the middle of a city, it would, well, wipe out the center of a city. But of course, the damage wouldn't just be limited to the crater itself. If you were standing anywhere within a few miles of this impact, then you wouldn't have had a very good day. And the reason that this impact was particularly bad is that this impact of this asteroid was mostly made of iron, and asteroids are made of a few different things, and I'll talk about this throughout this lecture. But iron is probably the worst thing you want an asteroid to be made out of if it's going to hit us, because these things really punch through our atmosphere, and when they hit us, they really make a big dent. But this is something that happened 50,000 years ago. So is this just something that used to happen, or are asteroids still hitting us, or could they hit us in the future? Well, let's look at something that happened a little more recently. So I want to talk about something called the Tunguska incident, or the Tunguska Event. So in 1908, there was a massive, massive explosion over Siberia in Russia. And at the time, no one knew what it was, because people did think maybe this was an asteroid impact, but the problem was there wasn't a crater. But what they did find is that every single tree in a huge, huge area had been knocked down. And that's what this photograph is actually showing us. This is all trees that have been knocked over. And millions of trees were knocked over by this explosion. In fact, we think this explosion was probably bigger than most nuclear bombs are. And we know now that this was an asteroid impact, but the reason it didn't make a crater is that the asteroid didn't make it to the surface. This is what we call an airburst event. And what this means is that the asteroid entered our atmosphere traveling 20 or 30,000 miles per hour. But when you're traveling that fast, just passing through the air is enough to heat you up to such an extent that for an asteroid, it can actually break up that asteroid. And in this case, the internal pressures in the asteroid cause it to break up explosively. And this caused a massive, massive shockwave, which knocked down all of these trees. Now, this was quite lucky, because if this happened just a few hours later, it would have come down over a populated area, and this potentially could have injured a lot of people. But again, this was over 100 years ago. And is this the most recent thing that we know about? Well, no. So just over 7 years ago, there was another airburst event over the Russian city of Chelyabinsk. It's always Russia, because Russia is such a big country, if you're wondering, by the way. And of course, because this happened in the modern era and it happened in Russia, the best footage of it all comes from dash cams. We also do have footage from security cameras and things like that, but it's definitely the most well-documented asteroid impact or asteroid airburst that we've ever seen. Now, normally I would show you a video here, but in my experience, videos don't work well over Zoom. So what I'll say is just go away and look this up afterwards. There are some amazing videos out there. And Chelyabinsk was an asteroid that was around 20 meters across. And when this asteroid exploded in the air, it did have the same energy as a small nuclear bomb. And this time it did do quite a lot of damage, and it hurt people. Most of this damage was in the form of shattered windows. So this shockwave blew out basically all the windows in the city. And all of that flying glass was obviously incredibly dangerous, and 1,500 people needed hospital treatment. So when I say 1,500 injured here, I don't mean 1,500 people had, bruises or stuff like that. I mean seriously injured. And this caused damage. It caused economic damage. It knocked down buildings, and it cost a lot of money to repair. And bearing in mind, $30 million of damage might not sound like much, but this is Russia, where things aren't quite as expensive. So that is significant damage. But perhaps the scariest thing about this is that we had no warning. For an asteroid that's just 20 meters across, we can't really see them coming. This just came out of the blue. So let's look at an asteroid that hasn't hit us yet, but might hit us in the future. So this is an asteroid called Bennu, and you may have actually heard of this asteroid because it's been in the news a lot over the past year. So this is one of the few asteroids that we've been able to send a spacecraft to. So NASA sent a little robot called OSIRIS-REx to go and explore this asteroid. It took lots of images, it made all sorts of measurements of the asteroid, and then last October, it actually touched down on the asteroid and scooped up a small sample of rocks. In fact, it's collected a few kilograms of rocks. And it's now bringing those rocks from this asteroid millions and millions of miles all the way back to Earth so we can use them in a laboratory and analyze them and learn more about what this asteroid's really made of. And the reason I'm interested in this asteroid is that this asteroid is actually a potentially hazardous asteroid. So it's around 500 meters across, and it has a 1 in 2,700 chance of crashing into the Earth in about 150 years. Now, 1 in 2,700 doesn't sound that bad. And some of you may be thinking, well, it's probably not going to hit us, so why should we worry about it? But when you really start to look into the damage that this could do, and then when you start to think about the probabilities more, you realize that we really can't afford to ignore this. Firstly, with an asteroid this size, if it hit us, it would be causing regional damage. So if this hit, for example, somewhere in Poland, we would be feeling the effects of it here in the UK. So an asteroid this big could be killing millions of people if it hit us. And a 1 in 2,700 chance of killing millions of people is, in my opinion, unacceptable. And if you're still not convinced, to put that into context, your chances of being killed in a terrorist attack in the UK are around 1 in 100,000. Your chances of being killed in a plane crash are around 1 in 20,000. And people are generally quite scared of plane crashes and terrorist attacks, and we have good reason to be scared of them. And as a society, we put a lot of resources and energy into making sure that these things don't happen. But the chances of this asteroid impacting the Earth are much, much higher than those things. And of course, the consequences would also be much worse. But of course, it's not just Bennu that we have to worry about. There are lots of asteroids out there that could hit us. But asteroids like Bennu, even though they're ranked as some of the most dangerous ones, they're not the ones I'm worried about. So as far as we know, no asteroid that's this big is going to hit us anytime in the next few hundred years. But what we don't know is what's going to hit us that's a little bit smaller. And the asteroids that I really worry about are the ones that are 20 to 100 meters in size, because these asteroids are so small that we just can't see them coming. And these hit us much more frequently. So a 20-meter asteroid might hit us a couple of times in a century. And you might be thinking, well, we just heard about the one that happened in 1908, which was around 50 meters. And we just heard about the one in 2013, which is about 20 meters. So we've already had 2 in the last 100 years or so. So why worry? We're not going to get another one for another 50 years. But that's not how probability works. It could hit us tomorrow, and we wouldn't see it coming. And if one of these asteroids fell over a city, or at least an urbanized area, then it would be putting a lot of lives at risk. So these asteroids are really something we need to be worried about. So hopefully you understand that asteroids are a real risk. But now we'll talk about how we actually find these asteroids. So how do we find the asteroids, and then how do we know that those asteroids might actually hit us? So here's another image I took with a telescope just a few weeks ago. And we're looking at a small patch of the sky. And once again, there is an asteroid hidden inside this image. But this time, I'm not going to show you where it is. I'm going to see if you can find it. So the way that we find asteroids isn't just by taking a single picture and then having an expert look at it and try and find the asteroid. What we do is we take a sequence of images that are separated in time. So I took this image, and then I took another image with the telescope pointing in the same direction about 15 minutes later. And as you can see, these stars haven't moved. If I blink between them, the stars are staying in the same place. But if you look very, very carefully, you might notice that something did move. I'll do this again. Something moved. And now I've got a third image, and I'm going to blink between them now. So the stars are staying still, but there is something moving. I don't know if anyone could see it. If you did, then well done. This is not an easy thing to do, but I'll show you where it is now. So this is it. So in the first image, the asteroid is down here. If I go to the second image, it's gone. And now it's up here. So in that 15-minute window, the asteroid's moved from down here to up here. Then I go to the third image, and the asteroid is up here. And so just by taking images and going back to look at that same part of the sky later on in a night, you can actually find asteroids just by looking for the only things in the image that are moving. Now, of course, this can be complicated by things like satellites, but we can filter those out quite well. But as I'm sure you're probably thinking, this would get very boring. I mean, even I'm very passionate about asteroids, but I really wouldn't want to sit there all day just blinking through images, looking for moving dots in the sky. And that's why the discovery of asteroids really started to explode in the 2000s, because people stopped looking for asteroids. Instead, we gave the job to computers. And now asteroids are mostly discovered automatically. So we actually have telescopes that are dedicated to discovering asteroids. So this is one that's actually still under construction. It's called the Vera Rubin Observatory. Now this one isn't totally dedicated to discovering asteroids. It's just one of the many things it will do. And this one's certainly going to revolutionize astronomy in many ways. But at the moment, most of the asteroids that we discover come from the Pan-STARRS network of telescopes, or the Catalina network of telescopes. And every single night, these telescopes, they open up, they point at a patch of the sky, then they move on and they move on, and they basically scan huge portions of the sky, sometimes even the entire sky in one night. And by revisiting those areas, they can find the things that are moving, and then they can find the asteroids. And now every week we are finding a few asteroids just from these telescopes, and there isn't that much human involvement. But the thing that I think is really cool is that this is all open source. Whenever an asteroid is discovered, it's actually announced publicly on this website here, which you're welcome to go and have a look at. It's called the Minor Planet Center. It's run by the International Astronomical Union. And whenever an asteroid is first discovered, it gets announced via this website. It's given a temporary name, and someone says when they saw it, where they saw it. And they also say which direction it was moving in and how quickly it was moving. And this is really important because the first thing you want to do when you discover an asteroid is work out how that asteroid is moving around the sun. Every asteroid in our solar system has its own unique orbit, and we have to calculate what that orbit is before we can know if it's going to hit us. And just from looking at it in one night, we can't work that out. And so by publishing these announcements on a website, other astronomers all around the world can revisit these asteroids over a period of days, weeks, or even months. And we can track and monitor asteroids for weeks and months, and then we can really constrain where that asteroid is going. And from that, we can then predict where the asteroid will be next week, next month, next year. And then once we've really got it accurate, we can actually predict where the asteroid will be hundreds of years into the future. And this isn't just something that professional astronomers do. There are actually amateur astronomers out there that help us confirm these asteroids and calculate their orbits. And I think that's something that's really cool because, this is something that may ultimately one day save the world. And it's not just, professionals and secretive stuff. It's all open source and anyone can get involved. Now, whenever an asteroid is discovered and we calculate its orbit, there are two separate systems that are used to calculate if that asteroid could impact the Earth. One of these is run by the European Space Agency, and one of these is run by NASA. And again, both of these are actually completely open. You can go on the websites here, which I've got at the bottom. And on these websites, they actually maintain a list of asteroids that could hit the Earth. There are a handful of asteroids that basically stay there at the top of the list. So if you can just see there, we still have 1950 DA and Bennu, which are ones I've mentioned. And then there are lots of other asteroids that kind of come and go because sometimes when we first detect it, it might look like it could hit the Earth. But then as we start to narrow down its exact trajectory through the solar system, we can actually rule out the chance of it hitting the Earth. So once we've found an asteroid and then we've recognized that that asteroid has a chance of impacting the Earth, we start a campaign to characterize that asteroid. And what I mean by characterize is we want to work out the most basic information about that asteroid. So we want to know how big that asteroid is. Obviously, that's very important because if we get hit by a 5-meter asteroid, that's not a problem. We don't have to worry about it. But if we get hit by a 5-kilometer asteroid, then that's something we really need to start worrying about. And the next thing is what's it made of? Because the size of an asteroid isn't the only thing that affects how much it could, how much of a catastrophe it could pose to us. Because asteroids, as I mentioned earlier, that are made of iron can cause more damage than asteroids that are just made of carbonaceous rocks and things like that. So we need to work out what the asteroid's made of. Then we also want to know what shape it is. And that's important because when we come to trying to stop an asteroid hitting us, we really need to know what the asteroid looks like, and we need to have an idea of how we might target the asteroid if we wanted to perhaps blow it up, or if we wanted to visit the asteroid, how a spacecraft might try to land on it. Then the next thing is if that asteroid's orbit is changing. And it turns out, unlike the Earth, which has a very, very stable orbit, some asteroids actually sort of drift. And as they go around the sun, every time they go around the sun, they may end up coming closer or further to the sun than they did the previous orbit or their previous year. And I'll explain how this happens, but it's very important because this tiny drift in an asteroid's orbit can actually make the difference between an asteroid missing the Earth or an asteroid hitting the Earth. So the very first thing that we do is take a light curve of the asteroid. And I've got a little animation here to show how these work. So what a light curve is basically a graph of how bright an asteroid is over a period of time. So here we have the graph on the right-hand side. So this line is showing us its brightness coming in from the right. And so the higher up it is, the brighter it is, and then it gets fainter. And we're just scrolling along through time. And here on the left, we can actually see the asteroid. Obviously, this isn't a real image. This is just a computer-generated model. And as this asteroid spins and tumbles, the amount of light that it reflects back to the Earth will change because it's presenting a different surface area to us. So here it's it's reflecting a lot of light, so it's bright. And then we look down the thin axis, it gets fainter. And by looking at these light curves, we can actually get an idea of what shape an asteroid is. So here's an example of a real light curve. This was taken by a telescope on Tenerife just a few months ago. And again, we can see an asteroid that gets brighter, and then it gets dimmer, and then it gets brighter again. And over the period of, for this asteroid, about 8 hours, this asteroid will vary in brightness. And the first thing you do when you see one of these light curves is work out how quickly that asteroid is spinning. And to do that, you have to have lots and lots of light curves and lots of very long light curves. And then you can actually look for a repeating pattern. And where that pattern repeats tells you where the asteroid has finished one rotation. And once we've done that, we can actually start to work out what shape the asteroid is. And this is something that I do a lot of. In fact, I spend about half of my time taking light curves, processing that data, and then working out what the asteroid looks like. We have lots of special software to help us do this. Normally, we might have 10, 20, even 30 light curves of an asteroid. And we feed these into the software, and this can give us an idea of what shape the asteroid is. And another thing that we can do is measure the brightness of the asteroid and use that to work out how big the asteroid is. Because we know how far away the asteroid is from the Earth, because we know what orbit it's on, we can actually work out how much sunlight it's reflecting to us. And that depends on how big the asteroid is. So just from taking these light curves, so just from measuring the brightness of the asteroid as it rotates, we can get a pretty good idea of how big the asteroid is. And we can also get a pretty good idea of what shape the asteroid is. But we don't have a really good idea. It's not perfect. It's just a loose measurement. Then the next thing we do is try and work out what the asteroid's made of. And using these telescopes, we can do this by looking at what color the asteroids are. Just like wood is a different color to metal, which is a different color to, say, a flower, things that are made of different materials are different colors. By measuring this in a telescope, we can work out what the asteroid is made of. So we can tell the difference between looking at something that's mostly made of iron or something that's mostly made of carbonaceous rock or silicon-based rocks. And we can get all of this just by pointing a telescope at it. However, if we want to work out more, and if you want to get a better idea of what the asteroid looks like, or if you want to get a better idea of how big the asteroid is, we can't use normal telescopes. We need to use something else. And this is where possibly my favorite part of studying asteroids comes in. So what we're looking at here is, or was, the Arecibo telescope. And Arecibo was a radio telescope, and for a very long time, it was the biggest radio telescope in the world. So this is kind of just like a satellite dish you might have on the side of your house. So this big dish effectively collects radio waves that are coming in from space, then reflects them back up to a receiver up here. Now, there are lots of radio telescopes around the world that do this. But what made Arecibo special was that Arecibo didn't just listen. Arecibo could actually broadcast radio waves out into space. And only one other telescope in the world can actually do this at the moment. And when you can do this, you can actually do radar. If you can broadcast radio waves to an asteroid, those radio waves will bounce back from that asteroid to the Earth, and then we can study that echo to work out all sorts of things about that asteroid, which I'll talk about in a second. But of course, Arecibo has been in the news recently for all the wrong reasons. So last August, one of these auxiliary cables here that holds up the instrument platform snapped. We still don't know why exactly. Arecibo gets a lot of earthquakes, a lot of hurricanes, so it certainly received lots of damage over the years. And after this first one collapsed, all the other ones were under a lot more strain, and then the next one snapped, and then in November, a third cable snapped, and eventually they all snapped, and then this entire platform came crashing down onto the dish. As it fell down, it actually swung around and hit the side of the dish. You can just see the remnants of it here, but it basically destroyed the dish in the process. Around 30% of the dish has been completely destroyed. The rest of it's been quite badly damaged. But rebuilding this is just not really possible. So unfortunately, they've taken the decision to demolish what's left of this telescope. And this is a really, really tragic loss for astronomers around the world, because this was the best radar system that we have for studying asteroids. And now we only have one other system left, and that one's nowhere near as good as Arecibo. It's only got 1/16 the power, and it can't spend as much time doing it. And this actually extends beyond, protecting the planet from asteroids, because asteroids aren't the only thing that this telescope is good for. This is also a tragedy for Puerto Rico, because this is a really big part of their culture. And if you meet someone from Puerto Rico, they're incredibly proud of this observatory. It supported the economy, it created lots of jobs, but it also inspired people. And a lot of the people that work on this telescope weren't flown in from other parts of the world. They grew up near the telescope and they fell in love with it and then ended up working on it. And so it really is a heartbreaking thing that we've lost this. But why is radar so special? Well, this is something called a delay Doppler image. Now, you're probably looking at this and saying, cool, I can see a picture of an asteroid, but this isn't actually a picture of an asteroid. Well, it is, but it isn't. So I know I promised I wouldn't be showing you many graphs, but this is actually technically a graph. If you imagine this x-axis here is this x-axis shows us how the asteroid is moving. So stuff on the right-hand side of each image here is rotating towards the Earth, and stuff on the left-hand side is rotating away from the Earth. So this asteroid's basically rotating counterclockwise. But stuff at the top is stuff that's closest to the Earth, and stuff at the bottom is stuff that's farthest from the Earth. So we're actually looking at this asteroid, not from kind of as we are looking at it on a screen right now, but this image was created by looking at it from the top. So we're looking down at it like this, along this axis, and this generates this image. And translating this into knowing what an asteroid looks like is quite complicated. It's certainly taken me quite a long time to get the hang of it, but we can do it, and we can use this to work out exactly what an asteroid looks like without having to go to it. So here's a really good example. It's an asteroid called Tutatus. This is, again, quite a scary asteroid. It's a near-Earth asteroid that may one day impact us. And on the left, we have a radar echo of this asteroid, and on the right we have a real photo of the asteroid taken by the Chinese Chang'e 2 spacecraft as it flew past it. And when we pointed the telescope, the radar telescope at this asteroid, we were looking at it at a similar angle to this. So looking at this actually gives you this in your radar echo. But to the trained eye, you can actually translate this shape into this. And that's exactly what we do. And again, we use lots of software to do this. In fact, we have to use supercomputers most of the time. But this is really, really a powerful tool, because sending a spacecraft to an asteroid costs millions, if not billions of dollars. Pointing a radar facility at an asteroid doesn't really cost much at all. We can count on our hands how many asteroids we've got photos of up close like this. But we've had hundreds of asteroids we've been able to see with radar to a very high level of detail. And we can even pick out craters and boulders on the surface. So it really is mind-blowing that we can do this. It still amazes me that while a conventional telescope just sees a point of light in the sky, with radar we can see individual boulders on an asteroid that's millions of miles away. And this is actually something that I spend a lot of my time doing as part of my PhD. So this asteroid that we're looking at here is kind of like my baby. I spent about a year developing a shape model for this asteroid based on a combination of radar echoes and light curves. And I've been able to work out exactly what this asteroid looks like. I've had to use supercomputers. It's taken me months and months and months of development to get to this stage, and it's still not quite finished. One interesting thing about this asteroid that I found is that because it's spinning so quickly, that explains why it's got this weird sort of bulge around the equator, and this is its equator. So it's spinning so quickly that it starts to bulge outwards because basically its gravity is not very strong, and so stuff starts to lift off from the surface. And this is really interesting because that means that if we keep looking at this asteroid and it keeps spinning up, we may actually see it break apart. So I'm very excited about what this asteroid could do in the next 2 years. But that's enough self-promoting for a moment. So going back to Planetary Radar and why it's useful. So it can tell us exactly how big an asteroid is, and it can tell us exactly what that asteroid looks like. And another thing it can do is very precisely tell us where that asteroid is. So just like you can use radar to work out where an aeroplane is or a ship is, this can tell us where the asteroid is more accurately than a conventional telescope. So we can really use this to hone in on the probability of whether or not an asteroid is going to hit us. And there are, of course, many more things we can do with radar, but I could talk for hours about this. Pictured here is actually the other radar telescope that I spoke of. This is in California. We call it Goldstone. And the only difference to this one is it can actually steer itself. So it can look at asteroids for longer than Arecibo could, but it can't look at asteroids that are anywhere near as far away. So it really is a big loss for us. So another thing I talked about was asteroids that have their orbit changing. And the thing, or one of the things that can cause an asteroid's orbit to change is the Garkovsky effect. And I've got a little video here. Hopefully it plays okay. And what it shows is an asteroid rotates. And as it rotates, it heats up and then it cools down in basically a day-night cycle. So I'm just going to see if I can control this video. There we go. So show you that again. So this asteroid is, oh, wrong way. This asteroid is moving through space. It's moving from right to left. As it rotates, the day side, which is pointing towards the sun, will heat up. And then as it spins around, points away from the sun, it cools off again. Just like it gets hot in the day on Earth, and then it cools off in the evening. But when an asteroid's cooling down, it does it by emitting infrared radiation. And this actually means that the asteroid experiences a very, very small recoil effect. And it's really weird to think of radiation or light giving you a recoil, but it happens. If you hold a laser pen and you turn on that laser pen, you are actually experiencing a tiny, tiny amount of recoil as you turn on the laser pen. Now, it's so small that you would never feel it, but for a small asteroid over tens or even hundreds of years, this effect can be quite big. And so the asteroid feels a recoil that pushes it back in the direction it's coming from, although it can also happen the other way around. And so in this case, the asteroid is being slowed down by the radiation it emits or reflects. And because it's being slowed down, that changes the trajectory it's on as it goes around the sun. And this is enough to make the difference between an asteroid hitting the Earth or an asteroid missing the Earth. Unfortunately, it's really, really hard to work out how much an asteroid is going to be drifting by because of this effect. And in order to do it, we not only need to know what shape it is very precisely, we also need to have an idea about its thermal properties. And at the moment, that's something that's still quite hard to work out. But just to kind of sum up the discovery and detection of asteroids, things are changing very quickly. So in the next few years, we're going to be launching a space telescope that's dedicated to discovering asteroids. The idea is we want to discover 90% of asteroids that are bigger than 150 meters. Currently, we're around 40% for that. And we're also building better telescopes down here on Earth. Hopefully, we're going to rebuild Arecibo. It will probably take 10 to 15 years, but there's already a bit of momentum. And of course, we're going to visit more asteroids. We're going to be sending more rockets and spacecraft to go and have a look at them and poke them with a stick, as I like to say. But now, going on to the, I guess, most exciting part of the evening, could we prevent an impact? So if we knew for certain that an asteroid was going to hit us, we do have a few options in our arsenal. Now, the first thing that everyone thinks of is, why don't we just fire loads of nuclear missiles at it? And yes, I will talk about that. But there are also some other very developed ideas about how we can prevent an asteroid from hitting the Earth. And this is something that we do train for. So every 2 years, there is an international conference where people from all sorts of different countries, both scientists and actually members of government, come together for an exercise where they simulate an asteroid impacting the Earth, and they work out what they would try and do. Here's an example from one of those conferences, and this is actually an asteroid that they've kind of made up that would hit the Earth in October this year. And they've got to work out in the next few weeks how they would stop that if it was real. Although I suspect the answer is they can't stop it. So let's start off with the obvious one, blowing up an asteroid. This is Hollywood's favorite solution to the problem of asteroids, although it's not necessarily the smartest solution. If anyone's seen movies like Armageddon, you'd probably envisage loads of nuclear bombs going off, blowing an asteroid into lots and lots of little pieces. But this isn't something we really want to do. The first problem is that this only works for really small asteroids. Even with the biggest nuclear bombs we have, blowing up an asteroid that's more than a few hundred meters across is just impossible. And even if you do blow up an asteroid into lots of pieces, that actually could make things worse, because instead of having one asteroid that's coming to the Earth, what you do is you turn one big asteroid into dozens or even hundreds of little asteroids. And if you don't know exactly what effect your explosion is going to have, what that could mean is you could take an asteroid that was going to hit the middle of the ocean and turn it into 10 asteroids, which are going to kind of hit the Earth like a shotgun and hit all over the place, and some of them might actually be a real threat. So nuclear disruption, as we call it, which is a fancy way of saying blowing up an asteroid with nukes, is really something that you'd only ever use in a Hail Mary situation. It's really not something that you'd ever want to do. But there is a better way to use nuclear weapons to save the world from an asteroid. And that's to take advantage of an effect called ablation. So this is the first of many terrible diagrams that I've created for this talk. And what we're looking at here is, if you imagine there's a nuclear explosion nearby to an asteroid, what it actually does is vaporize the surface of the asteroid. Now, most of the asteroid survives, but a thin layer sort of boils off. And this has an effect of acting like a sort of like a rocket engine. And the power of this explosion actually blows the asteroid away from the explosion. And this is the effect of this is that you can actually deflect the asteroid. You don't have to destroy it. You don't have to stop it. All you have to do is give it a bit of a kick, nudge it in a slightly different direction to the one it's currently going in, and so it will miss the Earth. And to kind of explain how this might work, so this is not to scale. I'll start off by saying, if we imagine here we have the Earth on a nice happy orbit around the sun, and then we have a big scary asteroid. So the Earth's going to come down here, and then the asteroid is on a trajectory to hit us here. We've found this asteroid and we know it's going to hit us. So what we do is we launch a little rocket. It's got one or several nuclear warheads on board and it detonates them. And the force of that explosion through the ablation effect will make the asteroid move in this direction. Now, it may only make the asteroid move by a couple meters. It may only slow it down or speed it up even by maybe 0.0001 miles per hour. But that can be enough to deflect an asteroid. And so after you've done this, the asteroid will be on a new trajectory, a slightly different one. That means it will miss the Earth. But let's say we didn't have as much warning. Let's say we only detected an asteroid just before it was about to hit us. If we tried to deflect an asteroid at this point, we would have to give it a much bigger kick. We'd have to have much more force to push that asteroid off course. And so what this really means is the key to protecting ourselves from asteroid impact is that we have to see these asteroids coming as soon as possible. We really want to know if they're going to hit us years and years or even decades before it happens, because if it's just a year or two before it hits us, we probably can't nudge it out of the way enough to stop an impact. But nuclear weapons aren't the only way to deflect an asteroid. So one of the most mature methods that we've thought up is something called a kinetic impactor. And this is basically a polite way of saying we want to crash something into the asteroid really, really fast and hope that pushes it out of the way. It's a little bit like just shooting the asteroid out of the way. And this has a few benefits. So firstly, it doesn't cause any problems with international law. At the moment, it's actually forbidden to send nuclear weapons to space, which is obviously a very good idea. But because we can't send nuclear weapons to space, we can't practice deflecting asteroids with them. But with kinetic impactors, we can practice moving asteroids around to see how well it works. And we've actually already tested this. I think I've got an animation here. Oh no, sorry, I don't. And there's a comet that was actually hit by something called deep impact in 2005. So we know that we can hit an asteroid, and we know that we can actually make the asteroid move. And in the next few years, there is actually going to be a mission to do this again. This time it's a much more focused attempt to practice deflecting an asteroid. And this is something that NASA's doing. It's called the Double Asteroid Redirection Test, or DART for short. And the target of this asteroid is, of this mission, is a double asteroid. So this is a model derived from radar data. And as you can see, there are two asteroids that we can see. So this is an asteroid called Didymos, and this is an asteroid called Dimorphos. And Dimorphos is a little bit like a moon. So Dimorphos actually goes around Didymos, just like our moon goes around the Earth. Dimorphos goes around Didymos. You can probably tell I'm getting a little bit mixed up around the names because until recently, this didn't have a name. So we all just called it Didymoon because, you know, Didymos and Didymoon, I actually think that's a bit more cute. And what the DART spacecraft is going to do is smash into Dimorphos at around 15,000 miles per hour. Now, this spacecraft weighs about 500 kilos. It's only about 30 meters across. That's if you're measuring the wingspan of its solar panels. And it will speed up the moon as it goes around Didymos. And it should speed it up to the point where its orbit becomes 7 minutes shorter. And this is why we're hitting a double asteroid and we're not hitting just a single asteroid, because we can use the way it moves around another asteroid to really precisely measure how much we've changed its speed by. And so we know how well we've deflected it compared to what we predicted. So this actually launches later this year, and it doesn't actually impact until towards the end of next year, but I'm certainly looking forward to it. One thing I forgot to mention actually is that we will get some footage of this impact because there is a smaller spacecraft that's going with it called Lucia, which is being built by the Italian Space Agency, which will be capturing the impact. And a few years after this impact, we're going to be sending a European Space Agency spacecraft to study the crater that we've left behind, work out how deep that crater is, work out if we've made the asteroid break up and if large chunks of rock are now floating unpredictably around, which is obviously something we don't want to happen. So kinetic impactors are certainly the most developed idea we have for stopping an asteroid hitting us. And I'm really looking forward to seeing the results of this test. There is one other kind of sensible option that we have, and that's something called a gravity tractor. Now, this is based on the idea that everything has its own gravity. I have my own gravity and I attract things towards me, but the effect is so small that you would never ever notice it. But when you're in space, you can notice this more because there's no air resistance to affect things. And so if you park a spacecraft next to an asteroid, the gravity of that spacecraft will actually pull the asteroid towards the spacecraft. Now, of course, this spacecraft will also be attracted to the rocket, but it has engines. And so it can start firing its engines and maintain distance. And so it's basically using gravity to tow the asteroid out of the way. And so this can also be used to deflect an asteroid. So I've thrown up a quick table of what our best options are for preventing an asteroid impact, depending on the size of the asteroid and when it's going to hit us. So if an asteroid was going to hit us next week, there's nothing we could do. And here I put civil defense. That's a polite way of saying evacuate and prepare for impact. If an asteroid was going to hit us in a year, we still wouldn't have much chance. Now, I imagine we would probably try to fire some nuclear weapons at it and maybe break it into smaller pieces, but we probably wouldn't really be able to stop it. And even with 5 years of warning, we probably couldn't stop an asteroid hitting us, regardless of how big or small it is. It's only when you have around 10 years of warning that you actually stand a chance of preventing an impact. And this is where kinetic impactors really start to become useful. So any asteroid below around 100 meters, we know that we should be able to deflect those asteroids just using technology that will very shortly will have tested. Of course, for the very largest asteroids in our solar system, our only option would be nuclear deflection. But this is something we would only do if we really, really had to, because there's so many unknown factors involved in it. Gravity tractors, they are a sensible idea, but towing something just using gravity obviously takes a very long time, and it only really works if you're towing something quite light, so smaller asteroids. And so you really need a really huge amount of time to do this. So only the smallest and most well understood asteroids with very distant impacts we could do this for. So there are a few other ideas that people have had to help us deflect or stop asteroid impacts. So one thing I haven't mentioned is reconnaissance missions. So our first visit to the asteroid might not be to crash into it or blow it up. It might just be to understand it better. If you're going to try and use a nuclear weapon to ablate the surface, you need to know what the surface is made of, because that will affect how efficiently it ablates. So reconnaissance missions are really, really important. And another thing that people talk about is various forms of directing energy towards the asteroid. So this could mean you point a laser at the asteroid and use that to ablate the surface and make it move away from the laser. Some people have suggested we actually paint the asteroid white. And if you remember the Garkovsky Effect, we can use this, if we paint it white or black, depending on which way we want it to go, we can change the way that the asteroid's orbit will drift just from it heating up and cooling down. One thing I hear people suggest a lot is, why don't we just strap a really big rocket to the asteroid and then use that to push it away? But the problem is, if you want to use a rocket to push it away, you have to take loads of fuel with you and then land that fuel on the asteroid. Now, if you're doing that, then you may as well have just used that fuel to speed yourself up and crash into the asteroid. It's not an efficient method, and unless you can reliably produce rocket fuel using resources you find on the asteroid, trying to just put a rocket engine on it and push it away doesn't really work. So this brings me more towards wrapping up. So the next few years or decades of planetary defense, there are a few key goals that we have. I think right now our priority is getting new planetary radar facilities. We need to replace Arecibo. It's urgent, in my opinion. And we also need to get better at discovering asteroids, particularly those really small ones, which are maybe 50 or 100 meters across, because these could hit us at any moment and we wouldn't see them coming. We also need to get better at preparing missions. If you want to go to an asteroid, you need to start planning 20 years beforehand. The DART mission, that's taken 20 years to plan. And unless we have 20 years of warning, we're not going to be able to deflect an asteroid. So we need to be able to put together a mission to launch and deflect an asteroid very, very quickly. Although, of course, there is a lot going on at the moment with new technology in space flight, so maybe we'll actually see that happen. And finally, we need to get better at working together. At the moment, the United States cannot work with China on anything to do with spaceflight. Just an example, it's actually illegal in the United States for anyone to work with China on spaceflight. And they have their reasons for this, but it means that it would be a huge barrier in a planetary defense scenario if countries just weren't working together on this. And this kind of brings me to the summary. If there's only one thing that you take away from this talk, I want it to be that it is inevitable that an asteroid will hit the Earth. It's only a matter of time. It's not a matter of if, it's a matter of when. And if an asteroid was going to hit us tomorrow, there is absolutely nothing we could do about it. We don't know that one's going to hit us tomorrow. It could hit us in 5 years, one could hit us in 100 years, or even 1,000 years. We just don't know when the next big, dangerous asteroid is going to come along. But we only have one Earth, so I don't really want to take our chances with it. And I think this is a good opportunity to learn from our past mistakes. So let's look at the elephant in the room, COVID-19. For decades, scientists have been saying that a new virus is going to emerge and create a pandemic, and it's definitely going to happen. We just don't know when. They said it's not a matter of if, it's a matter of when. There will be a pandemic, but we don't know when it's going to happen. And it did happen, and because people didn't really listen to the scientists, we weren't ready for it. And now look where we are. And then you look at climate change. We've known about that for decades, but people just didn't really want to listen to the scientists. It seemed a bit inconvenient to have to deal with it. And again, now it's already too late to prevent some of the damage. There's already lasting damage, although of course there's still a lot we can do. And I think we need to learn from these mistakes. And when it comes to asteroids, again, it's something that will happen. We know it's going to happen, but we can stop it from happening if we choose to. Of course, I myself cannot control that. It's something that we as a society need to recognize and act on together.